Hello everyone. Thank you for being here for the presentation. I am Sudesh Singanamalla, a first year PhD student in the Information Communication Technology for Development Lab at the University of Washington, Seattle, advised by Professor Curtis Heimerl and Professor Richard Anderson. Curtis is on the call today. I'm here to present about some of our recent work in decentralizing LTE authentication and enabling roaming in telecom, especially community cellular networks. This work is in collaboration with Esther Jang, Nick Duran, Matt Johnson, Spencer Sevilla, and Curtis Emerald. So let's dive in. There are approximately 1 billion people today who live outside mobile broadband coverage, and nearly 400 million of these people live outside any mobile coverage. Telecom operators have rolled out 2G and 3G networks as far as they're commercially and economically feasible for them to do worldwide. Therefore, there is this need for improving rural connectivity with networks which are self-sufficient and can be managed by the community. Over the past few years, our lab has been actively working with field partners to deploy community cellular networks. Community cellular networks are small-scale independent cellular networks, which consist of single base station attached to an edge network core. These types of networks are optimized for local needs, can be run cooperatively, and are sustainable in rural areas, providing the users with local services. However, community cellular networks do have some challenges. They're severely constrained by backhaul satellite connectivity and intermittent power supply in these regions. Additionally, the single tower only has a specific coverage radius, and users could quickly move out of network connectivity range. So why are we doing this? Why can't telecom companies set up the infrastructure necessary to improve connectivity in rural areas and provide them with internet access? What happens when these community members move out of the network zone between different communities? Traditional LTE networks, as mentioned before, are not economically viable to extend and deploy in remote rural areas. They're primarily profit-driven and cannot cater to local desires in the community, such as free local calls within the community, managing the community's YouTube content, for example, and additionally, roaming between networks is a challenging problem. Telecom operators today enter into business agreements to allow users of one network to roam on another network operator's infrastructure and be provided with the connectivity. But this is a problem with an exponential complexity. Every single telecom operator has to have a roaming agreement with at least one mobile network in each country to allow their users to roam. Many countries don't allow national roaming too. This business operations complexity can be handled by large telecom operators in each country, but cannot be handled by smaller telecom operators or community cellular networks. This brings us to an important question. Can we provide cellular data access in remote rural areas, and can we enable these users in community cellular networks to roam between communities with a shared understanding? Before we go into how we tried to answer that question, let me take you through a quick introduction to the LTE networks. An LTE network is an end-to-end all IP-based network which consists of two parts. The first is the radio access network, which is the collection of base stations and wireless communication infrastructure. And the second is the enhanced packet core, or the EPC, which is the core network to which these radio access networks are actually connected. The LTE network architecture is a large complex beast, and the interoperability of these networks worldwide is due to the standardization of the protocol by GSMA and 3GPP. Of course, a core part of the ecosystem is the user equipment, which are standard off-the-shelf mobile devices, which are LTE capable and can support connectivity in different LTE bands. The eNode B is the radio base station, which provides a radio link interface between the UE and the EPC core network. The MME, or the mobility management entity, is a part of the EPC and in traditional cellular networks present in data centers. These handle various operations like user authentication, signaling, session management for every particular device. The serving gateway is a system that routes and forwards user data packets and allows traffic management. The packet data network gateway is the gateway which provides internet connectivity from the user device and is capable of performing policy enforcement and lawful interception. The HSS, or the home subscriber server, is a database server which contains user-related information and security information related to SIM cards, data limits of the user, type of subscription, limits on the subscription, and other information for network operators. While there are other pieces to the LTE architecture, we can strip the entire system into a series of microservices and have these pieces put together to create a minimal functional LTE network. In the community cellular networks, this essentially moves the traditional data center network EPC to the edge. In our deployments, these run on low power Zotac boxes with a reasonable amount of memory. They're inexpensive and actively support hundreds of users in Bokondini, Indonesia. We use and actively contribute to the development of Open5GS, a C implementation of the LTE protocol. Now that we understand the pieces, the LTE authentication procedure is a protocol that is used to bidirectionally authenticate user devices to the network and validate and authenticate the network to the user device. This is generally done by a pre-burnt symmetric key in the SIM card provided by the telecom operator. We'll get to it in the later slides. What makes roaming complex is the need to authenticate a user who does not belong to the network and grant them access to the network infrastructure. Typically, this is done by tunneling all the requests from the roaming network to the subscriber's home network, which results in higher latencies. Another way would be to exchange the symmetric keys between the telecom operators over an encrypted channel, which raises serious security concerns. Additionally, this needs the network cores to be fully available and connected when a user device connects to the roaming network. The authentication should be done by the home network, and the roaming network trusts that the home network has done the authentication correctly. Though this solution works in today's world in commercial LTE networks, this is particularly problematic in community cellular networks, which are disconnected and challenged by power failures and failures in backhaul connectivity. We are constrained to not change the authentication mechanism since these are protocols that the hardware manufacturers have built into phones and are optimized for it. We need to make some interesting changes instead to the core network. The SIM cards follow a specification and are manufactured by a lot of third-party manufacturers. The authentication algorithm used is millinage and relies on symmetric key cryptography with 128-bit AES encryption. Every SIM card provisioned contains a symmetric key, which is stored in the SIM and in the telecom operator's database. And other fields like the international mobile subscriber identity, sequence numbers, and authentication management fields are used to compute different authentication values that are used during authentication. Sequence numbers are particularly interesting because these are one-time use values which are organized into a matrix by mod32. The mobile device uses the sequence numbers in a specific row vector every time it needs to authenticate and join the network. Once a vector is used or skipped, it invalidates the value and the values preceding the sequence used in the row vector. These SQN numbers are actually a concatenation of 27 bits of the sequence numbers, SEQ, and 5 bits of the index value IND. For example, if the UE attaches with a sequence value of 0 the first time and it follows up with the usage of 64, the value of 32, which is in the row, will be invalidated and cannot be used. However, the UE could use values from multiple row vectors without sticking to a specific row vector. This happens during synchronization failures when the HSS server and the UE need to establish the state of the new sequence number. The LTE specification provides multiple functions called F1 and F2345, which is basically a collection of 4 functions F2, F3, F4, and F5, which have the same inputs and are used along with a randomly generated value called RAND to compute the fields, which are the MAC, the expected response, which is XRES, the corresponding anonymity key, AK, integrity key, IK, and the cipher key, CK. These are issued by the HSS to the MME, which is signaled to the user device during the authentication protocol. Let's actually step into the authentication workflow and understand what is really happening behind the scenes. The user device connects to the eNode B, which forwards the request to the MME in an attached request. The MME could request the user device to identify itself using the IMSI number or some identity number provisioned in the SIM card and creates a temporary identity for the user device on the network. Since at this point the MME does not actually contain any state relevant to the identity which it had validated, because it has not validated it previously, it requests the HSS using the diameter protocol for some authentication information and provides the identifier information of the user device. The HSS server at this point validates this request and checks its database for the existence of the user with an identity and uses the symmetric key that it has corresponding to that user, computes the millenage functions, and generates the values of F1 to F5. Now it does this by using a random value RAND, which is issued as a challenge, and it shares the AUTN and the RAND values, which are along with the expected response and the key integrity value called KSME to the MME. What you see here is a security design where the knowledge of the LTE symmetric key corresponding to the subscriber never leaves the HSS. This tuple of values highlighted is shown as the authentication vector. The MME removes the expected response and the KASME values and challenges the user device to prove the identity using the RAND and the AUTN values in the authentication request. This information is signaled back in a downlink transport request to the user device via the eNode B. The user device validates this information in the AUTN, confirming the validity of the network, and computes a response, RES, using the symmetric key on the SIM card, which is sent back in an uplink transport request as the authentication response to the MME. The MME validates this response and compares it against the expected response which is provided to it by the HSS. Once this initial authentication is established, the UE and the EPCs establish a security mode and derive the necessary integrity and cipher keys based on the device capabilities using the KASME value, thus completing the entire authentication exercise and allowing the user to attach to the network. The KASME, or the Key Access Security Management Entity, depends on the identity of the SIM and is derived by both the user device and the HSS. The single-use SQN vector or the SQN values in the row vectors, along with having the LTE key of the subscriber, allows the community cellular core, in our case, to pre-compute the necessary authentication vectors with arbitrary RAND values, which can be shared with other community cellular networks. When a user visits the new network, these values can be issued by the local network core, even when the home subscriber network core is unreachable or unavailable. To make this happen, we connect multiple community cellular network cores as peers over a consortium blockchain, and each home network computes and publishes a fixed number of vectors to its peers in the network. In Hyperledger Sawtooth, which is the blockchain we use, these values are issued as transactions which are sent by the home network core to its peers. The peers regularly compute blocks of transactions and achieve a common state for each subscriber who does not belong to their network. A roaming network can cache in the authentication vectors to enable the user to roam onto the network and perform billing settlements later. We currently have an implementation of this system which generates a rolling window of n usable authentication vectors and shares it across the network of peers with a pre-attached monetary value to each authentication vector. We run these experiments in lab settings using a mini SDR radio and a low-powered Zotac mini computers running Open5GS and the sawtooth blockchain nodes. The current benchmarks are run with serial processing of the transaction information, and we see roughly 4 transactions per second. This is, of course, a very naive benchmark, and we've identified optimizations which need to be made to improve the efficiency of this system to achieve Sawtooth's benchmarked hundreds of transactions per second performance. What we do notice is that blockchain consensus protocols are extremely chatty and consume lots of bandwidth, which is scarce resource in community cellular networks. There is a need to be able to tune these network parameters to minimize their chattiness. Over the next few months, we are rolling out some of the optimization updates into a real-world deployment with the Othello network in Seattle, allowing users to successfully roam between community cellular networks while still being able to be connected to the network and have internet access. Thank you so much. I'm open to questions.
Now we see presentation mode.
Sorry?
Now we see the presentation mode. What is you?
Okay, I don't know. Let me do that. Okay.
I think you got swap displays now. Top buttons, then it will work.
That's better?
Better.
Yep.
Thank you.
Okay. All right. Hello, everyone. My name is Yanis, and I am going to present a high-level overview of the interplanetary file system, which is IPFS. I am a member of Protocol Labs, which is running, which I developed and is running a number of different projects, IPFS being one of them. All of these projects, IPFS, libp2p, IPLD, and all the others I'm going to talk about today are open source projects, community driven, and they have a very big user base that is developing and using those projects. So IPFS is a decentralized storage and delivery network primarily. You can kind of think of that if you've not heard of IPFS or haven't used IPFS before. You can think of that as a decentralized Dropbox, for example, where you have several different peers that are contributing their storage to the network. So the fundamental principles of IPFS is peer-to-peer networking, which we all know from the past, and content-based addressing, which also many of us in this group have heard about before from work like the DINRG group and the like. So when talking about IPFS, as I said, one of the primary things is to kind of replace or enhance HTTP, the HTTP protocol, and make it work in a peer-to-peer fashion. This is done as an effort to convert centralized services of today's internet into decentralized and distributed services. There is a momentum behind the Web3 community where people want to build services that do not have to have a trusted intermediary, as is the case with most of the applications that we're using today. So the problems that have been identified and that IPFS is not necessarily solving itself, but wants to develop a protocol stack that is going to address those problems are around censorship, the fact that some ISPs might catch, cut internet access to people in some specific country. There is huge inefficiency, as we all know, when we want to stream or download some popular piece of data, that this is being streamed several different times and as many times as the requests to the network are. the internet of today is not working in an offline mode, and so on and so forth. So if we have a distributed network which is based primarily on peer-to-peer connections, then we kind of were able to make things better, make the network more resilient, offline first, increase scalability and efficiency, improve privacy, and become trustless as high-level targets. So the second principle that IPFS is building on is, apart from peer-to-peer that I just mentioned, is that IPFS wants to move what is happening with HTTP, which is location addressing, to content addressing. So we see in this example that instead of having to go to DNS and go through the infrastructure of today, that is managed by some centralized entity, not necessarily the ISP only, but other entities as well. We want to have a content address, and that address directly the content that some user wants to access. So IPFS is a stack, is a protocol, is a kind of a protocol stack that has several different components. One of them is libp2p, which is a library for peer-to-peer networking, is the networking stack of IPFS. There is IPLD, which is stands for the Interplanetary Linked Data, which is a data layer for addressable content. And there is multi-formats project, which also is combining those IPLD and libp2p in providing rules to format data and data requests as they travel through the network. So some key facts about IPFS is that there is no central server, it's totally peer-to-peer based. The content that users are that exists in the network is not pushed into some user's device, but instead it is being pulled when a user wants to make when a user makes a request for a content. You can store and retrieve any type of content within the IPFS network. And it's also worth noting that there is there is a single IPFS network, but it's a protocol stack that someone can fork and basically build a private IPFS network. So it's a protocol stack rather than a network in itself. It's got many different use cases and many different companies and initiatives that are building on top of it. It is used for decentralized video streaming. It is used for decentralized distributed sound and music streaming. There are many different applications that are building on top of it, and basically they all explore, use and utilize IPFS and the main components that build on top of it for storage and for peer-to-peer connectivity between users. So we're going to go roughly through the life cycle of content within IPFS, from adding files to getting files. And through this, I hope it's going to be made clear what kinds of applications can actually use IPFS, or how can someone, make a private network and use IPFS for their own application. So what is happening when we want to use IPFS? There are basically two parts. There is the content producer or content publisher, which is when you want to import some content into the IPFS network. Then you have to name the content, and then on the other side, as a consumer of content, you want to request and get some access, get access to the content that you're interested in. So on the left-hand side of the screen, we see that most of what is happening is part of the IPLD project. On the right-hand side of the screen, on the content consumer side, where we have peer and content routing, where it's mostly about the libp2p project. And multi-formats the multi-formats project is standing somewhere in the middle and is getting principles of both, combining them both, as I'm going to mention in a minute. So the first thing that someone does when you want to use the IPFS system is that you get a file and you have to chunk it into different into different chunks, individual chunks. Now, all those chunks, they get their own content address, and this is done for three main purposes. One is for deduplication, or to avoid what is also called redundancy. So if you have two parts of a file or two parts of the folder being the same file duplicated, then you don't need to have two copies of the same file. This means that when someone is asking for the file, they don't need to get 2 times the same file. But it also means that when something is delivered but is not delivered correctly, then you don't need to ask for the same for the whole file again, but you can ask for the particular piece that has been corrupted while in transit. So each chunk of the file, it has got its own content address, which we're going to mention in a minute what exactly it consists of. So how does IPFS deals with content addressing? So we can think of files having some content identifier. Here we have file A, B, and some folder, and each one of them, they have their own CID, the content identifier. Then you have the same way that in the file system, you have folders that are basically including files in them. What you have in IPFS is basically a root CID. So the root CID is containing several different chunks of the same file or several different files of the same folder. Folder is, at the end of the day, a different kind of file, so therefore that's the representation if we want to see it in that form on the right. So IPFS is building on the naming part, at least, is building on Merkle DAGs, Merkle directed acyclic graphs. So these are data structures basically where each node along the tree is content addressed. So here we have, for example, a node with information about 2 users, and then each of the users has got inside the folder or this data structure, they have different different files that represents content that belongs to this user. What this gives us is that we can easily go from location-based identifiers to content-based identifiers. And this, as we know from previous years, is a very powerful concept because it can improve a lot the efficiency of how we request and distribute content in the network. Now, here comes the component of that is called IPLD, the interplanetary linked data, as I mentioned before, which is the data layer for content address data. And what it achieves is that when you have some piece of content, this piece of content is signed and has got its own CID, and therefore, independently of whether it belongs to some Merkle tree, it is an individual entity, an object of its own, and therefore it can be used in any other different data structure that the user wants to use it. So, for example, if we have a structure where we have CID and some data about a user, one of them being a payment, then these can be directly used, for example, by a blockchain as a transaction message. So the same thing can be used into several different data structures, and this makes the whole thing much more efficient. So we want to go from location-based addressing to content-based addressing, and to do that, there is the content identifier, or the CID, which I'm going to cover relatively briefly. It looks something like that. I mean, these are 2 different versions of a CID. They are self-describing, and basically they are hashes with a bunch of metadata. So they are immutable, so they come as a hash digest of some content. Therefore, this cannot change. The name is going to become permanent. This doesn't mean that within the IPFS network, when you add something, it is going to stay permanently there. It is instead going to mean that this CID is going to stay the same, because once we change anything in that object, the whole CID is going to change. It is verifiable because it is signed with the private key of the publisher, and therefore it can be checked whether some content that some user has requested and has received, it is what the user actually requested for. The combination of these make the system trustless because it is a pure peer-to-peer content addressing network. This is a structure of what CID looks like. I'm not going to go too deep into the details, but basically we have a multi-hash, there is a multi-codec, and there is a base, which each one means they are connected through multi-formats. As we said before, this is a set of rules that is connecting the IPLD and the libp2p projects. So the multi-hash is basically a hash with some metadata. The multi-codec is some specific codes that describe whatever the user wants to describe. So it could be a version of the protocol, it could be IPv4, IPv6, it could be the version of the transport protocol that the users want to use, but it could be something as arbitrary as a name or an identity. And there are several different codes to express these different kinds of things. Now, the multi-hash is basically the hash digest together with its length, and a multi-codec which shows which hash function has been used in order to hash the content that the user is requesting. Okay, finally, there is the multi-base, which is the encoding that is being used. And the reason why there has been all of that put together is that there needs to be some kind of what is called future proofing. So if we hash something with some particular hash today, and in some years from now we don't want to use the same hash because there has been found some problem with it, can be broken or anything, then we can directly change the hash function without having to change the whole of the CID. It's just meaning that we're now using a new hash function, and therefore the CID, the hash of the content, is going to look different than what it used to be before. Now we have talked about content identifiers, and this is, as we said, there are several different benefits that come with it. One of them is that it is immutable. This is good in some senses, but of course, as you can understand, is but in some other senses, because if someone wants to update the file, frequently want to do when we're using anything that has to do with the internet, the whole CID changes, and therefore we have to update all the records of everything to point to the new version of the file. This is achieved in IPFS with something called IPNS, and it stands for the Interplanetary Naming System. And what this does basically is that instead of linking the CID to the content itself, it actually links to the public key of the publisher. So if you want to publish something that you know you're going to want to change in the future, you do not hash the content itself, but you hash the public key of your peer, and that's what you're publishing to the network. Then once you want to, of course, you associate the content with the hash of the public key, and therefore you can always publish new versions of the same content under the same public key, and that's what is going to stay and be delivered to the users. Now, if we go to the second part, which is now we're getting onto the other side of how do we request things from the network, we have to enter the project, which is called libp2p, and it's a modular peer-to-peer networking stack. And the purpose of that is to get us from the content address and the CID that we have talked up until now to get to the location address and basically go and eventually find the peer that is storing some content. libp2p is a decentralized process addressing library which can locate, connect, and authenticate basically any process that the user wants. This is done through cryptographically derived public keys, and the benefit that this has got is that even if some process is changing its point of attachment, is moving around, or is mobile, it's not going to affect what is happening, and the fact that this peer needs to be still routable and still findable in the network. libp2p has got several different components. It's a modular networking stack, and it can support several different transports. There is a pub/sub protocol, not traversal, but most importantly for IPFS is peer and content routing. It is worth noting here that libp2p can live on its own. It doesn't necessarily have to be part of what IPFS is building on top. And it can be used as a peer-to-peer library outside of IPFS in any standalone peer-to-peer system. So here is an example of one of the features of libp2p, which is the multi-addresses. And it points to what we have seen before, where we have several different components of the multi-formats of a given request, and how this is basically put inside, is routed through the network. So here we can see that the path is built, but with multi-addresses, it can encode the fact that this connection is using the IPv4 protocol. This is the IP address. It's using TCP with that port number, and so on and so forth. And then there is the content identifier of the content that the user is looking at. So this is this comes in byte format, and this makes it very efficient. But this, can link, two peers together when they start a communication to fetch some content from one another. So in terms of routing, in a peer-to-peer network, as we know, peers need to be discoverable, they need to be routable. The IPFS and libp2p projects, they obviously, as you can imagine, they're facing issues with NUTs and NUT traversal. There are several different ways that you can navigate through a NUT and find other peers, but there are also different kinds of IPFS nodes. There could be an IPFS server or an IPFS client node, and the difference between these two is that the client is only requesting things, whereas the server is also providing storage and caching to the network and is accessible, is discoverable from the network. The way peers are structured in IPFS is through DHT, so the distributed hash table, which is, as we all know, a key value store, which is pointing peers towards the hash table as the hash space is split between the different peers. So here down on the right bottom part is an actual IPFS DHT table where you can have the key value store from CID. It can point to some IP address, or from an IPNS public hash of a public key. It can point to a CID in the IPFS world and make the connection between these two. So in terms of what flavor of a DHT IPFS is using, it is using the Kademlia DHT. I'm not going to go too much into detail. The main point is that Kademlia is very efficient in terms of jumping through lots of peers in order to get as fast as possible to the CID that a user is requesting from, and is also making parallel connections to several different peers in order to avoid some peers being offline and therefore having to wait for a timeout. Don't forget that at least the current version of IPFS is a pure peer-to-peer network, therefore nodes can come and go and the churn rate is very high. Therefore, there are many undialable nodes, not only because of NAT traversal, but also because users have gone offline. Okay, yeah, that's just a visual representation of how Kademlia can jump the hash table and go faster towards the destination. Of course, there are problems here in terms of an overlay, because the DHT is always an overlay, and this is obviously always suboptimal in terms of routing. One hop on the overlay network can be several tens of hops in the underlay network, and therefore there need to be some optimizations there to try and find content as close as possible to the users. And there are extensions to multi-layer and hierarchical DHTs to improve performance on that respect. Now, finally, there is another simple protocol which is called BitSwap, and is actually operating in parallel to the DHT. And what it does is that if there are two different users that want to, they have two different want lists, as they called, and in there is a list of things that each user wants, and those users, they are exchanging their want lists, and they're trying to find, you know, whatever the other peer has got, they're exchanging the actual content. BitSwap is utilizing all of the connections that a peer has got. So not only any connection that the peer has seen through the DHT or other means, through bootstrappers or any other knowledge that it has got about some other peer in the network, it's going to basically ask everyone with the want list of the particular user. And this is done in order to improve performance, and okay, of course, there is a subsequent bandwidth cost because there are several different requests sent out as compared to the DHT that are only a few. So in summary, when publishing content in the IPFS network, you have to first chunk the content, calculate the CID of the content, then add the content to the network, which does not mean that if a user is adding content, that this content is replicated elsewhere. It means that the user is making available the local memory of its own node, and he's basically putting in the network a provider record. The provider record is the one that is replicated across several different peers in the network according to the hashing function and the peer ID. But the content is not replicated, the content stays locally. The content is only replicated when other users are requesting some piece of content and are therefore then caching the content as well. So this is this part of consuming content as an IPFS peer, where you have to get to know the content identifier of what you're looking for, and this is external to the IPFS system itself. It's happening out of bound. Then you have to do the usual DHT walk or get content through BitSwap. And then what peers do is that they're saving a local copy in their own cache, and therefore they can then serve as a provider to other nodes. In parallel, there are other extensions where instead of having to become a full node or a client node on IPFS, users can consume content through the browser. There are already several different browser extensions that support directly IPFS, and so directly means instead of putting HTTP : / you can put IPFS : / and then put the IPNS or IPFS record, the hash the content you're looking for, and the content is going to provide you back with the network is going to provide you back with what you have asked. This is happening. This is done through something called IPFS Gateway, which are basically normal DHT server nodes. And what they're doing is that they're propagating a request that comes from the browser to the DHT network itself. So in this pretty quick presentation, I hope I kind of made it a little bit clear what IPFS is, and the fact that it's not a kind of project on its own, but it relies on several different other projects, some of them being IPLD, libp2p, and multi-formats, and the blending between them. So there are several different, there is documentation available for both IPFS and libp2p. There are interactive tutorials that someone can go and learn how to do all these step by step. There is the IPFS companion browser, which means that you basically, it's just an add-on to the browser, and you can participate in the IPFS network without having to do anything else, and several other small bits and pieces that users can use to use the network, but also build applications on top of it. This concludes the presentation. Thank you very much. I think I didn't run over time hugely.
Not so much. Thank you very much, Dennis.
Okay, thanks.
And
to answer any questions, yeah.
Yes, you will have to. Actually, I understood the purpose behind the Q+ Q- protocol. So that actually allows us to see who's asking questions. So sometimes we can't really understand your name. And so please use that. And we have a first question by Jörg.
Yeah, Jörg Gott. Hi, Janis. Very nice overview talk. I am trying to put two things together in my mind, and maybe you can help me. Maybe I missed something in the middle. At the beginning, you talked about the interplanetary file system and very much about distributed and potentially disconnected offline first activities. Yet in the end, you're using Kademlia and a peer-to-peer network which relies on understanding which nodes are around and which aren't around to keep structure and so on consistent. So one relies, one wants to be disconnected, the other one relies on being connected in order to perform all kinds of operation. How do you reconcile these two?
Yeah, that's a very good point. So basically, the current version of IPFS is not directly supporting, at least not through the DHT, is not directly supporting offline communication. So there is a relatively big effort and appetite within the IPFS ecosystem to have nodes communicate with each other in an offline manner, the way that you know very well. This, of course, is not linking to the rest of what I said with the DHT. This will have to be a separate part that is going to be communicated through the libp2p platform. So the libp2p platform, for example, could say that I don't want now to communicate through IPv4 or whatever. I want to communicate through Bluetooth, and that's the transport that I want to use in order to communicate with others. And in that sense, you know, there's not going to be any involvement of the DHT or anything like that. It's going to be only Bluetooth with, you know, whatever API is running on top to connect nearby devices.
But it seems the information maintenance, distribution, and so on problem remains, right?
In the local network, you mean?
Especially in the non-local network, if you have occasional connectivity between different nodes. How do you differentiate a node having finally died from a node being not available for 2 days?
Right. The node will have to reprovide. So what is happening? So this comes directly from Kademlia and comes with its own set of problems. Every node in the network that wants to provide some content, I want to host the file on my laptop and provide it become an IPFS node. I have to provide to give a provider record to say that I am here and I am hosting this CID. If I go offline, this has to be done every 12 or 24 hours or something like that. So if I go offline for 2 days, I'm not going to provide this record, and therefore, if I am the only one that has this content cached, then no one is going to be able to find it in the network. Now, this doesn't mean that it, yeah, sorry.
Go ahead.
Yeah, this doesn't mean that in these 2 days, if I can communicate with other people over Bluetooth, I cannot provide the content locally. Of course, there is no, at least no kind of stable way of making your local peers find, publish and consume content locally. But it is something that can be built on top of libp2p, and it's a very interesting direction to have.
Yeah, we have been banging our heads on this ourselves. This is why I'm asking. So maybe this is more for an offline discussion. I'd just be interested how you manage ID space if in a network that is partly disconnected, but maybe we can take that offline too.
Yeah, so once the node comes back online, it's going to provide the records, and it's going to get connected back to the network. How this happens in the offline case, yeah, I don't have a clear view. I think it's not very well developed within libp2p, but I'm very happy to, yeah, let's discuss about this.
Okay, cool, thanks.
Thanks.
Okay, thank you. Are there
Any
other
other
questions?
questions?
Okay. Let me put myself in the queue. So, I mean, this clearly seems to be targeted at file sharing type of applications. So, what happens with all kinds of real-time interactive applications? Is that totally out of scope, or what's the idea with IPFS?
Right, so that's a good point. So ideally, as you say, yeah, the main point is storage and delivery of content. So you can think of that as a kind of very centralized peer-to-peer CDN kind of thing. But there are, I'm aware of the general thing, but not the details of more interactive things, that applications that have built on top of IPFS. Now, the mechanics of this, to be honest, I'm not aware, but I can imagine that it's going to be, some storage with, the CIDs and all these parts that I have talked about, and some hooks through libp2p, which is going to make the whole thing interactive. But I don't have further details. But extensions are possible, but they are certainly not optimized at this point.
Okay. Yeah. Okay, great. Thanks, Dennis.
Thank you. I'm happy to answer any other questions or give pointers offline. Reach out to me. And thanks a lot. Thank you.
Very good. Thank you.
Thank you. Stop sharing.
Okay, so next would be Gareth Tyson. Challenges in the decentralized web.
Can you hear me okay?
Yes, we can hear you.
Super. Let's see if I can share this screen.
Good. Yep, looking good.
Perfect. Okay, hi everyone. So hopefully everybody's safe and well at the moment. This is going to be a new experience for us all because this is, I think, the first time I've presented at IETF meeting from my bedroom. But also there'll be a new experience because the last couple of talks are some really excellent technical presentations on new and emerging technologies, whereas what I want to do in my slot is actually present a measurement study that we recently published at IMC, looking at some of the challenges in the types of decentralized web technologies that Yanis was just talking about. And what I hope to do by the end of the session is persuade you that it's damn hard to decentralize the web. Now, I'm not the first person to make this observation. People probably recognize this chap here, Alexis de Tocqueville. So he was actually a French historian philosopher, and I think about 150 years ago now, he made the following statement: a push towards decentralization in the end just became an extension of centralization. So at this point, I would usually ask the audience if they can guess what he's talking about, but that's probably not going to scale through this medium. So I'll cut to the chase. He was actually referring to the French Revolution, a very bloody time where the people of France tried to decentralize the head of Louis XVI from the rest of him. And in many ways, this is not so dissimilar to what we've been studying in the decentralized web today. So to go through a bit of a TARDIS time shift and return to the 1990s, we can think about how the web used to work. And it looked very similar to this. You had a bunch of servers scattered all over the world, and those servers were running their own respective websites. So maybe, you know, this one was a forum, this might have been a blogging site, this might have been a search engine. And you can see each one of these services have their own respective groups of users. Now, this was in many ways a really cool model because, of course, you had much more symmetrical power structures. You could argue there was more resilience because there's lots of different replicas of servers. And you had no central points of failure. So, for example, if this server went down, it didn't necessarily impact these other two. And for anybody who's concerned about privacy issues, naturally, this model also distributed data around the world, so you didn't have a single data store holding everything. Now, if you fast forward to the day today, what you see is actually a very different model, where you have large organizations such as Google or Facebook, which operated servers which essentially aggregate the entire world's user base. Now, it's sort of fashionable at the moment to criticize these models, but I think probably most people on the call would also agree that there were a bunch of benefits to this type of model. So, for example, you had a critical mass of users. It's really cool that if I, for example, flew to Mexico and met somebody, I'd be able to add them on Facebook and interact with them just as easily as if I were to meet them as a next door neighbor. Economies of scale and the orchestrated deployments also mean that we get very reliable services, very well engineered services that are constantly innovated and bringing us new cool technologies. So these are the two extreme ends of the spectrum of how the web has worked over the last 20 years. And I suppose the question that the decentralized web folk, and I suppose DINRG more broadly, wants to answer is, how do we go about trying to get the best of both worlds? Now, I'm coming from London in the UK, and probably most of the people on the call are aware that we've been experimenting with this problem ourselves recently. And what we've mostly found is that trying to get the best of both worlds in these negotiations often doesn't work particularly well. So what I want to do now is segue into the actual technical part of this presentation, which is related to this decentralized web concept. So we already know one technology very well, and that was IPFS, because Yanis was just presenting extensively of it. But IPFS is not the only technology out there. And what's happened over the last couple of years is decentralized federated versions of all the popular services that we know and love have become available in the open source community. So, for example, this one over here is called PeerTube. That's a decentralized version of YouTube. Diaspora is an old social network. That's obviously a decentralized version of Facebook. And this one over here is the one we're going to be talking about today. That's called Mastodon. And that's a new decentralized version of microblogs, so like Twitter. So before moving on, it probably makes sense for me to briefly explain how Mastodon works. So let's just imagine for a moment that we wanted to get involved in this process and set up our own Mastodon instance. So what we do is, of course, we'd first go ahead and we'd buy ourselves a server or maybe a virtual machine in Amazon. And all we'd have to do is install the Mastodon software. So Mastodon is basically a full web stack. So it's got the entire package that you can install onto the one machine. And that's a web server with all the backend and so forth installed to give you your own little microblogging service. So it's like a mini version of Twitter installed on that server. Of course, other people around the world can be doing this as well. So maybe this one is based over in the United States and there's another one that's based in China. And each one of these can start to accumulate their own user groups. So it might happen if I were to set up a DINRG server and I could maybe advertise on the mailing list, and all you come along, you click on the link, you can access through your web browser the Mastodon service, and then you can create your account and start microblogging. There's only one problem here, which is, imagine, for example, Daniele, who some of you might know, is using this server, and John, who some of you may know, was running that server. Now, one of the really nice things I mentioned before about Facebook is that wherever you are in the world, if you use Facebook, you can communicate. But in this model, you can see that you have these three separate islands of communication. So if John and Daniele wanted to communicate, the way Mastodon allows you to do that is through something called a federated follow operation. And what that means is Daniele can follow the user on another account. And actually what that means in practice is a federated link gets established between these two servers, such that whenever John publishes a post, Daniele's server automatically pulls it across. Now, Mastodon's been going for a couple of years now. What you can imagine has happened is whenever one of these remote users publish the post, the server pulls it across and locally represents it to any remote users. And this is something that now means that all of these servers are actually meshed together. And this is why we call sometimes this the Fediverse, simply because these servers are federating together. And this is a very different model to the one that Yanis was describing, where he had a traditional DHT approach. In this case, we don't have DHTs and indexing. In fact, what happens is that these federated links start to look a little bit more like a social network, where you have servers following each other. Okay, so at this point, you might say, well, fantastic, you've got this federated model. That's great, we've decentralized and things are working well. The only problem is, however, that old Alexis de Tocqueville comes in from the left and says, actually, no, you've not. Because even though you've built a decentralized architecture, and this decentralized software is capable of running in an entirely decentralized fashion, there are certain pressures that continue to exist that push you back towards a more central mode of operation. So we thought this was a really interesting phenomenon to look at. So what we started doing was measuring Mastodon. So we basically set up a distributed measurement infrastructure that spent basically 18 months connecting to all of these servers, pulling down both the toots. Toots is the Mastodon equivalent of a tweet. Those are the microblogs, as well as the different federated links that were connecting them at any point in time. We were doing this every 5 minutes, and we were recording the content, but we also were recording things like performance and availability properties of the servers to see if they were still online. And what we wanted to test was whether or not there were some pressures that were pushing this setup back towards centralization. Now, what I want to do for the rest of this slot is go through essentially a thought experiment. And if this was face-to-face, this thought experiment would be led by questions that I was posing to you guys. Again, through this medium, that's probably not going to work. So let's kick off with a simple one and say, if you were to set up your own Mastodon server, where would you host it? Because this is typically the first decision an administrator has to make. Where do they put their server? So what we did was take a look at the 4,000 servers that we're looking at in Mastodon and resolve the IP addresses that we saw back to the autonomous systems and the countries that were hosting them. And what you can imagine was to find is a very skewed distribution, where we find that over half of the users using Mastodon using servers based in just 3 networks. And when you take a look at the content, that gets even worse. So 2/3 of all the content being hosted by this platform are hosted in just 3 autonomous systems. And again, this raises question to what extent this decentralized architecture is actually being used practically in a decentralized way. So that's from the administrator's standpoint. Another question you might ask is, if you were a user wanting to start interacting on Mastodon, which of these instances would you join? Because in the central Twitter model, when you want to join the platform, you just subscribe to Twitter. There's just one service you link to. But in Mastodon, what you actually have to do is create accounts on all the different instances. So you have to make a very conscious decision, which instance is of most interest to me. So we took a look at this, and what we found was that actually 90% of all users have joined just the top 5% of instances. In fact, that top 5% of instances host 95% of all the microblogging content. So again, that raises questions how decentralized this is in practice when you see that just removing 5% of those popular instances would wipe out nearly every user in the system. So a natural question you might ask here is, well, what's driving this? Why are people joining such a small number of instances? So one of the reasons that we found was that there's a very skewed popularity distribution when looking at the topics covered by these instances. Because what tends to happen in a federated model is each administrator who sets up an instance does so with a particular topic in mind. So that might be technology or music or education. For example, what we see is that a large number of instances get set up about technology. So this blue bar here represents the fraction of instances in the global network. And you see that over half of them are all about technology. But there's an elephant in the room here because we have this red bar over here. And the red bar represents the fraction of users in the system. And actually what we find is that the vast majority, almost 60% of all the users, are subscribing to essentially adult content platforms. So instances that are dedicated to sharing adult material. And again, this pushes the idea of how this is not such a decentralized system in practice because the topical interests of people are really driving the trends here. So the next thing you might think, well, okay, fair enough. These social patterns are driving the model back towards centralization. But maybe because we had a decentralized architecture, that makes it more reliable. Because just as Yanis was saying before, having a centralized model means, even if peers in the CAD network go down, the whole system continues running. The only problem is the federated model that I'm talking about, which actually makes up the majority of the decentralized web, doesn't work in the same fashion. So just to remind you what I mentioned before, we were connecting to all of these Mastodon servers every 5 minutes. And what we found was that 11% of the instances we were connecting to were inaccessible for at least half of the time. And when I say that, I don't mean that they, spent the first half of the measurement period online and then afterwards they went offline. No, it wasn't like that. What you got instead was this pattern where they're becoming online and offline repeatedly. An obvious hypothesis to test here is, well, maybe those ones that are unreliable just don't happen to have many users. So perhaps that's because the administrator's not done a good job of their instance and not attracted many people on there. So what we're doing here is we're just separating the Mastodon instances based on the number of users on that platform. So you see down here, for example, we're looking at instances that have got fewer than 10,000 users. Actually, what we see is indeed, in that case, the downtime is substantially higher than instances that have, say, 1 million users. And that makes sense because obviously if you've got 1 million users, you're probably an administrator who's taking really good care of your server. What's more interesting is the fact that actually you get a number of outliers, such that even servers that have managed to accumulate over 1 million users spend in excess of 20 or 30% of their time offline. So the next question to ask yourself is actually, why does this happen? So why are these instances going down so regularly? So there's actually a diversity of reasons here, too many to mention. But a few of the interesting ones we saw was that in many cases, there are still some central dependencies in the system. Even though at the application layer, we've actually built ourselves a decentralized model, down at the network layer, it's not the case at all. So I mentioned earlier that a lot of the instances were hosted on just a small number of networks. And what we actually found here was that across the period, you can see through these spikes, we got entire network outages. So we we saw 6 cases of entire networks going down. And when they did, they ripped the entire set of instances hosted there out of the system. Another really interesting one that we saw, and this was a little bit unexpected, is that the majority of instances are using a single certificate authority. So the reason for that is that this particular certificate authority gives free certificates out. So 85% of the instances were just attracted by that cost saving. The only problem is that this particular certificate authority only gives quite short time to live, so 3 months. And what we saw in just one day, 105 instances having their certificate expire. Now, what you can see quickly is that people notice that, and the administrators start renewing their certificates, and the number goes down. But after 3 months again, because the 3 months expiry date triggers, you get this spike. And again, this is just one example of how central dependencies in the system can take down big chunks of it. So the final thing I want to touch upon is the complexity that basically you folks do. So you users, you people, because people have this horrible tendency to act like people, and people tend to have central dependencies in themselves. So let me show you what I mean by that with a quick analysis. So imagine you've just joined one of these instances. So you've just created your new account. The first thing you need to decide is who are you going to follow? Just like on Twitter, when you join it, you need to decide the account you want to follow. So what we find is that the top 5% of users accumulate the vast majority of followers. And in fact, about 60% of all of them get fewer than 10 followers. And this means that you have basically lots of users like sad, lonely Mr. Pigeon, who nobody wants to follow, and a very small number of very popular users like Grumpy Cat, who everybody follows. Now, at first, this might sound natural because we know that's how the social networks of the world work. But the complicating factor in Mastodon is, what happens if Grumpy Cat's server goes down? Because if Grumpy Cat's server goes down, he suddenly gets severed from the network. Now, the initial thought you might have is, well, that's a bit inconvenient because if he gets severed from the network, people can't see his posts. But it's actually much more complicated than that. Let me show you why that is the case. So imagine we've got 4 Mastodon servers, and you can see they're hosted in 3 different networks. So each of these Mastodon servers have their own independent groups of users. Right? Very straightforward. Now, because these aren't connected, if, for example, a user over here wanted to connect and pass a post to a user over here, what you'd have to have is a social network that connects them. So this is an example where maybe this user is following that user through a remote federated operation. You can see this user is following users over here. Now, naturally, this means that if one of these posts were to be pulled across the network, across these users, down in the network layer, you can see federated links would happen across each step. So if this post wants to pass on between these 2 users, obviously you'd have to have some connections going at the network layer. Okay, straightforward. Now, the only problem is that this is not how a real social network looks like. It looks much more like this, where you have some very popular users over here. You might have some very unpopular users like this one here. And importantly, you might have what's called bridge nodes. This is this user. We call this a bridge user because you can see he connects 2 different communities together. And the only problem is, what happens if we have a problem in the network? Maybe there's some BGP error or some network failure. And because of that network failure, the federated link gets severed. Well, what that means is the bridge user suddenly gets partitioned from the network and the whole social network fragments. And when it fragments, it can have real ramifications for the communication flow between servers. Now, you can see how serious this is by looking at this simple graph. So what this graph does, along the x-axis, it's showing the individual instances. Along the y-axis, it's showing the percentage of content on that instance, which comes from its local users in blue versus its yellow users, which are remote. So what you see is some of the big instances actually get lots and lots of home content generated. So that means on the instance itself, most of the content is being generated. But what we quickly see is that the vast majority of servers are entirely reliant on remote toots. 78% of the instances produce under 10% of their own content. So they really rely on those federated links for pulling in remote content from other users. We thought we'd play around with this. What we did is we recreated the social graph and we recreated the underlying federated graph. And then we just did a few simulations to remove servers to see what would happen. And what we then did was we computed a couple of graph metrics. So we computed the size of the largest component, and we computed the number of strongly connected components. So I don't want to go into too much detail about how we did this, but let me just summarize a couple of the main points. So the first one is that if we remove servers with the top 1% of accounts, all of a sudden, the largest connected component in the social graph depletes from actually the vast majority, about 90% of the nodes, all the way down to about 26% of them. So in other words, the graph just fragments and none of the users are able to communicate with each other. So imagine that in your own social network on Twitter. Imagine if all of a sudden 75% of the people that you're used to receiving content from suddenly become unavailable by just a small error in the network. The other experiment we tried was removing entire networks. And remember, this has a big ramification because when you're removing a network, it actually kills all the nodes inside it. So actually, when we remove just 5 popular networks, the social graph, the follower graph, just shatters. It shatters into over 270 small components. So in other words, you can still communicate with a few people, but all of a sudden you realize that the majority of your social graph, the majority of your followers that you're used to talking to cannot be reached. And the same thing happens for content. So this is showing what happens when you remove top autonomous systems and top servers. And again, I don't want to go into too much detail about these graphs, but what this line shows is that as you remove top networks, the amount of content that stays in the network collapses radically. So by removing the top 10 networks hosting instances, you find that almost 90% of all the content gets removed from the system. And again, this is a product of the centralization, because when you have such a central dependency, removing those central dependencies have a disproportionately large effect on the system. So what we thought we could try and do is fix this problem through replication. So the idea was when a content item gets created, like a microblog, what we could do is we could automatically copy it from that home server to another one, such that if the home server goes offline, we still have the replicated copy in the network. So the first thing that we tried was to actually do this based on social replication. So in other words, if one user follows another one, that instance would automatically copy all the content from the other one and store it persistently on itself to make it available if the home server went down. And what you see here is that this now performs much better than these previous graphs without replication. So the curve is much more shallow. So even if you're removing autonomous systems, the availability in the system still stays much, much higher through here. But even though we say that, there's still a significant drop. About 20% of the content becomes unavailable still, even though we're doing this social-based replication. And the reason is these popular servers tend to cluster together. So users tend to follow users on other servers that are hosted in the same network, potentially in the same region. By replicating it onto another server in the same network, it's basically redundant, it's useless. So the network goes down, both servers go down, and the content gets lost. So finally, what we tried to experiment with was doing actually random replication. The random replication detaches the replication process from those social biases that I described earlier. This is the same graph as I showed you earlier. This is without any replication. You can see as you remove instances, the amount of content in the system drops dramatically. This is what happens when you have the social replication. So again, it's a bit better, but still, with a large number of instances removed, you get a big drop because of the social properties that we're seeing with users in the same network. But with the random replication, you actually get fantastic replication. So you get in excess of 99% availability simply because that random replication finally detaches the replication process from the underlying social graph that's causing so many of these troubles. Anyway, hopefully I didn't go on for too long there. The main take-home message, as I was trying to get across to you, is that actually building these technologies is fantastic. And I don't want it at all to sound like I was criticizing Mastodon, because I think the design and the way it works is actually pretty superb. The main message I was trying to get across instead was that when you build these systems, even though you build them in a decentralized manner, it doesn't necessarily mean people will use them in a decentralized manner. Anyway, if you're interested in reading more about this, I've put the paper reference at the bottom, and of course, I'm happy to take more questions now, and please feel free to drop me an email if you want to follow up separately. Anyway, but thank you for listening.
Great. Thank you very much, Gareth. Are there any questions? Please use the Q+ protocol. Yanis.
Okay. Yeah, sorry. So I've got two questions. One of them is technical and has to do with if you know any details, if you recall, on how do the different servers actually exchange this federated remote thing that you mentioned that I can remember.
So
it must be some sort of pub/sub protocol, or is it just out of curiosity?
Yeah, that's exactly what it is. So it's a pub/sub protocol. It's been standardized through W3C, and it's called ActivityPub. And
okay,
you know, it works in the way that I basically described. So it's a web-based protocol. One server will connect to another one, and it will issue obviously pull requests for the content of interest of the local users.
Yeah. Okay, and then another quick question. I mean, towards the conclusion that you had. So, okay, now, at least in terms of infrastructure, you said that people are using AWS and Cloudflare and whatever. So do you think that if other decentralized technologies that can use like decentralized computation platforms and things like that, you know, could move the whole thing away? Because in a sense now it's difficult. There are very few such technologies that are still building their products, and therefore even if you wanted to use them, it could be difficult. I don't know personally, but I could imagine that it could be a little bit more painful than using, you know, Amazon as a quick kind of solution. So do you think that as those develop, you know, technologies are developing in parallel, and therefore at some point they could converge and, you know, have a decentralized application that is running on a decentralized infrastructure?
Yeah, so I think it all boils down to basically ease of management, because in many cases, the reason people gravitate towards things like AWS is because they're just very easy to use. For example, in the case of Amazon, you know, there's a really nice tutorial available online. And that sounds very simple, but I think in many ways, those are the things that administrators are attracted to. So if you were to offer a sort of a decentralized underpinning, which could be set up and managed as easily as just setting up something on Amazon, then I'm sure people would take it up. The other thing I should say is that there's no constraints that mean you have to put your servers on cloud platforms. In fact, you could host it anywhere you want. You could put it in your basements for all the system cares. It would still work in an identical fashion. The other thing I should mention is that the Mastodon implementation also has things like replication supported in its back end as well. So I was simplifying some of the messages, and I'm very happy to follow up offline on this if it's useful. But there are back-end replication schemes that you can use to ensure that, let's say, data doesn't get lost if you have a failure in your front end.
Okay, interesting, thanks. Yeah.
I think the other important thing to drill home is that the model here is what I would describe as instance-centric. So the most important concept in Mastodon is the idea of having an instance that an administrator controls and other people can connect into. So as long as the underpinnings that you built that were decentralized allowed that administrator to still control and manage their own instance, I don't think there would be a sort of philosophical problem with changing the model. If it were to suddenly mean that administrators lost control, then I think there'd be probably a significant pushback from the people who run the system. Simply because the centralization isn't only about the users, it's also about the administrators having the freedom to set up and control their own Mastodon community.
Okay. Next would be Jörg. Jörg.
I was not in the queue.
Sorry, that's your queue. Yeah, okay.
I was just started, or oh my God, what did I do? Do I have to give a talk and don't know anything about the slides or something?
Yeah, I was just testing you. No, sorry. Then I think Melinda. No, that was me. Okay, sorry. Then I think we are done. Sorry, it was. Any other questions? So okay.
Thanks, everyone.
Gareth, one more question. So it seems to me that like the most important, if you want, say, problem or deficiency in Mastodon that you identified was the lack of replication. Really, is there anything else that came to mind when you looked into it? So any other lessons learned that how you would maybe optimize it in a second system?
Yeah, I mean, certainly the replication is probably the principal one. So the replication I was referring to at the end of the presentation was mostly about kind of content replication. It was principally about availability. And obviously, as we all know, in distributed systems, availability is only one of the desirable properties. So another common problem is performance as well, because obviously you've got relatively small numbers of servers potentially hosting lots of users. So another systems innovation, which I think would be quite sensible, would be replicating also for performance, such that you could offload load onto underutilized servers. And actually, that could be quite easy to do because these servers are all over the world, right? They're in the US, they're in Europe, they're in Asia. So actually, when servers in the US are heavily loaded, you'll have servers in China which are not being used at all simply because of the time zone difference. So I think there's a lot of potential for actually federating not only the content on these servers, but also the resources, such that during periods of high utilization for servers in one locale, you can call on the resources of another one. The other system innovation that I think would be quite useful was a little bit more integrated support for discovering new users, because in the way that the federated model works, essentially you have to pick which instance you're going to join. It'd be quite difficult, particularly if you're new to the system, because you don't know all the users out there. So having better integrated search facilities where you on your local instance can easily search for content on instances around the world would actually make the discovery and the exploration much easier in Mastodon. And I think this is where the type of things Yanis was talking about could come into play, where you actually underpin a lot of this with a DHT, such that you can replicate indexed information about which users and which topics are supported, so that you can easily find new instances to interact with and new users to interact with, even when they're not registered on the same server that you are. I'm sure there are a bunch of other ones I can think of as well. Need to have a follow-up chat on it as well.
Okay, yeah, sounds interesting. Thanks a lot again.
Cool. Thanks everybody for listening.
Okay, and next will be Shigea.
Can you see my slide in the?
Yes, but in presenter view, so you.
Okay. Let me. can't find a way to switch to.
Last time I did this, I did it on separate desktops on macOS, but
Okay, okay.
difficult to explain.
Let me stop first.
Do you have the PDF by any chance, or?
Maybe that works. Working well?
It's not better.
Okay. So let me provide the update on our activity on the establishing a healthy ecosystem for decentralized finance.
Yeah. So we still see the presenter view. We still see the presenter view. At least I.
Nope, you don't.
Okay,
Fine
then.
now.
Okay, not for me then. Okay. Okay. Yeah, go ahead then.
So it's a we just established a group called the DINRG, which is the abbreviation of the Blockchain Governance Initiative Network. And let me describe quickly on that activity. So I have mentioned several times that DLT is still young compared to the internet, but the impact is not negligible now. And the financial regulators start understanding both excellent and adverse impact of DLT. So in the past 2.5 years, Keio University, Georgetown University, and the Japanese Financial Services Agency jointly worked together with BSafe Network to discuss how we can help create healthy ecosystem. JFSA guys learned how internet technology developed and deployed, and we learned how financial regulator works. So we launched the group because the regulators had a positive reaction in the G20 communique. So we launched a group called Begin on March 10th this year. So what is Begin? Begin is an open and neutral forum to deepen common understanding and to collaborate to address issues they face in order to attain sustainable development of the blockchain community. So we want regulators, consumers, open source style engineers or tech guys and the businesses get together to improve or advances health ecosystem of decentralized finance. So currently we have 23 contributors in multiple stakeholders groups, and let me show that we have several engineers, several people from government and regulators, and from various academias, and from financial industries, and also standard and expert group and the civil societies too, and also internet pioneer like a Pinawan. So the goal of the Begin is creating an open and global and neutral platform, multi-stakeholder dialogue, to create a developing a common language and understanding among the stakeholders with the diverse perspectives. So, so we've also tried to provide academic anchors, which internet technology people have, with a trustable document and the code based on the open source style approach. So the key activities will be the creating a folder and host meeting to reach to the variety of the stakeholders and the creative outcomes by rough consensus, contribute to the public policy design and implementation. There's a lot of things we are going to do. So how it works is currently we are trying to use very similar to the open source approach. So we have we already hosted the various documents on the GitHub, and we look forward to have a contribution to our documents, which is very in early stage. So we only have a set of documents which describe our concept. So, and we are trying to establish various working groups to do various discussion, not only technology, but also the governance of this group itself. So we had tried to have a physical meeting in March, but due to the coronavirus things, we failed to do that. So we did panel discussions on some of the key persons and broadcasted through internet, and we announced the launch of the group. So we will do some ad hoc online preparatory meeting for the begin block 01 in this April, and we try to have physical meeting in the autumn and early 2021, but we are not sure, of course, due to the recent epidemic. So current documentation is available on the website, and this site has a link of all of the document and mailing list we have. And the initial document set is available at the GitHub URL. So we are looking forward to have help from the tech community like IETF and IETF. So we are trying to launch at least the 2 working groups on the working group on the build begin community itself, and a study group on the key management, identity, and the privacy issues, which is our primary focus to do things at this moment. So also we are looking forward to have get the proposal on the new activities or a new group, a new working group. So please check out the Genesis document, and also on the TOR document, which describe what we are going to do in detail. So please contribute to this document or get in touch with us. Please send an email to the Begin contact at the Begin team, or join to the Begin announcement list from this URL. That's it for now. Thank you very much.
Okay, thank you, Shigeya. Are there any questions? So the best way to get in touch with that group is to subscribe to the mailing list. Is that correct?
Yeah, announcement or get in touch with us via this Begin contact or to me. That is easiest, I think. So my email address is on the last page of this slide.
Okay, great.
Also, I'm going to send out the information on the IETF at the IETF too, soon, possibly today.
Okay. Very good. Then, yeah, thanks for informing us. Thank you very much. Okay, so this brings us to the end of the program for today. So just a quick an announcement. So Melinda and I were discussing about a potential physical face-to-face meeting in June, which obviously doesn't make much sense to plan right now. So there's nothing to announce in that regard right now. So we will have to monitor that situation and we'll see what we can do. So in general, the idea was that we would hold an interim at an academic conference and also say engage with other people who may not normally attend IETF meetings. And so that's still the plan, but obviously right now it's just too unpredictable. So yeah, let's see. We may have another online meeting depending on things will develop. So in the meantime, yeah, please use the mail list and let's see. We can maybe exchange more information and have more of discussion there. Thanks again to all presenters today. Thank you for being in that meeting today. Hope to see you soon in the near future. Please be safe. Thank you. Bye-bye.
Thanks for organizing.
Thank you.
Yeah, thanks, Dirk. Take care.